NED Library, absolutely autonomous education. We are technocrats, astute entrepreneurs, and above all, passionate academics. We are education specialists, rendering learning solutions to schools, corporates, and government, such as a broad spectrum of digital learning environments. We are the bridge between students and teachers. Our role is complementary. Our focus area is the curriculum, how well suited it is to the industry's skills demands. Reading seemingly is a handicap. How well adjusted is the content to fit to the target audience? There is always a way for a fish to willingly take the bait.
Hello, I'm Zinas Rebwa from NED Library, and our motto is absolutely autonomous education. I shall be taking you through a process of photosynthesis known as the light independent stage, which some wrongfully call the dark stage, and the other name for that is the Calvin cycle. So, before we get into the nitty-gritties of that, I'm just going to give a brief background to the subject in question, photosynthesis, that we're talking about. You realize that everything begins off from the goal of life is to make energy, and energy, our source of energy is light. And isn't it surprising to notice that when God created the universe, the first thing that he said was, let there be light. So everything about life, as it were, has got to do with light. So, having said that, we have gotten to an appreciation that the goal of life is to create energy. And what do we need the energy for? You realize that the product of photosynthesis is our glucose molecule, and of particular interest is our molecule glucose. What we are trying to do right now is to find a relationship between the light independent stage and the light dependent stage. And you realize that glucose, as it were, is a fuel molecule. When we say fuel, in other words, it contains the carbon, the element carbon. So having said that, we move on to the issue, because the goal of photosynthesis at the end of the day is to produce this important molecule, which is the source of fuel for all the processes that goes on in the cell of living organisms. The glucose is needed for respiration, and respiration is where we get our energy to carry out the processes of life. So begin to realize that the glucose molecule from our light-dependent stages, we ended up with these two important molecules. The oxygen was evolved. Of course, the oxygen is useful for processes such as the respiration, what we shall get to cover in the next coming topics. But as for now, we want to know the fate of the two molecules, the two important molecules that we encountered during the light-dependent stage, and that is particularly our ATP molecule and the NADP molecule. So, as guided by our slide here, you begin to realize that the Calvin cycle, which is the light-independent stage, is made up of those 5 processes, which is carboxylation, hydrolysis, photosynthesis, carboxylation, hydrolysis, phosphorylation, reduction of our NADP, sorry, this is supposed to be NADPH molecule, and the regeneration of our Iubp molecule. So what exactly are we talking about? This is what we're going to be delving into shortly. What is carboxylation? So let us go back to our equation of photosynthesis. And I'm just going to simply outline the word equation of our photosynthesis. We are talking of photosynthesis is whereby you are taking in raw materials such as carbon dioxide and water, like the way I say word equation, water, and then what we end up with is glucose plus oxygen. This is evolved to be used for processes such as respiration, which the plant also undergoes. It is not only humans carrying out the process of respiration, even plants themselves do undergo the process of respiration. But now we understand, we know where our water is coming from, and we want to see how the carbon dioxide is utilized as far as synthesis of our glucose molecule is concerned. Okay, fine. For the sake of explaining photosynthesis as a redox reaction, the molecular structure will kind of simplify the harder for us. So we have our C6 H12 and our oxygen 6 here, and we want to look at these two molecules to begin off with. We're looking at carbon dioxide and we're looking at the glucose molecule. And here we see that we have oxygen, and we are moving on. What have we added to our carbon dioxide molecule? We have added hydrogen. So according to redox reaction, when we add hydrogen into a molecule, what have we done to it? So in other words, addition of hydrogen is reduction. That is how the photosynthesis is termed as redox reaction. Enough of that being said, we move on to the crux of our bulletin, which are the stages involved as far as our dark reaction is concerned. So the first thing that we seek to understand is carboxylation. What does it mean when we say carboxylation? Carboxylation, like we say, this is a cycle. It is starting from this point. Carboxylation is, we have got our molecule here, which is known as Iubp, which is a 5-carbon molecule. Simply, the molecule consists of 5 carbon atoms. And then you have got your Iubp reacting with carbon dioxide, and it forms a molecule which is a 6-carbon molecule, and the name is too complicated to pronounce. For now, we just call it a 6-carbon molecule. It's formed at the end of the day, and this molecule is unstable. And this is a very unstable molecule. But now, as we go down with our presentation, you realize that there is a summary to the whole processes that is going on. What we have is we have got. I want for you to take note of this equation. It is vital to some of the explanations, especially when it comes to the issue of the regeneration of your Iubp molecule, which is an important molecule as far as the Calvin cycle is concerned. What you have is here is your Iubp. Your 6 molecules of Iubp will react with 6 moles of carbon dioxide to produce what is known as 12 molecules of PGL when all is said and done. And in terms of configuration, this has got five carbons. Iubp is 5 carbon molecule, and as you can see, carbon dioxide has got 1 carbon, and then our PGL is a 3 carbon molecule. And as far as these reactions are considered, you know that we are supposed to observe the law of conservation of energy. Nothing is supposed to be destroyed along the way. So if we try to check out whether our right-hand side is equivalent to our left-hand side, at the end of the day, we have gotten everything correct. So that you will realize that here we're saying that we have got 5 carbon molecules and 5 carbon atoms, and then the process of the generation of the PGL requires 6 moles of the Iubp. At the end of the day, we are saying that we are dealing with 6 times 5, that's 30 carbons this side. 30 carbons plus, we are saying that we are dealing with 6, for this reaction we need 6 molecules of carbon dioxide. So 1 carbon times 6, it gives you 6. So this is our right hand side. This is our left hand side. We have got 36 carbons. We want to check whether the law of conservation of energy was observed. Then here we are saying that we have got our PGL is a 3 carbon molecule. So this is 3 times 12 molecules of PGL. And what we have at the end of the day in this reaction, it's involving 36 carbons. And as you can see, we have observed the law of conservation of energy. We have got 36 carbons formed here, and the 36 carbons here formed. Yeah, this stage is important as far as the regeneration of the Iubp molecule is important, since this is the initial phase of our light independent stage. So the first stage, as we have explained, is the carboxylation, which can be called carbon fixation, and the enzyme that is responsible for that is rubisco, for fixing our carbon dioxide as it reacts with Iubp. And now, from what I have alluded to earlier on, the molecule that is formed when Iubp reacts with carbon dioxide is very unstable. So this leads us to the next stage, which is hydrolysis. Hydrolysis, as you can see from the presentation that we did on light-dependent reactions, the lysis part of it refers to the breaking down. So what we want to achieve at the end of the day is to come up with a molecule which is stable. So what happens there is addition of water is going to break down our 6 carbon molecule into the first stable products of our light independent stage, which is known as our PGA molecule, which is a 3 carbon molecule. That is important to understand. That is why it is called hydrolysis. Hydrolysis speaks of breaking down of a molecule. So we have broken down a 6 carbon molecule into a 3 carbon molecule known as the 3-PGA. Now, as you can see from this part, as we move on from 3-phosphoglycerate molecule to the third molecule, which is 1,3-bisphosphoglycerate. What is happening here is we are investing into it. We need energy in order to come to this particular molecule. So what is happening is we are saying that we have got the PGA molecule is reacting with ATP, and then what we have at the end of the day is a molecule called 1,3 biphosphoglycerate, BPG. Okay. I'm not going to write the full name for the sake of our space. And also what we have here is a DP formed. But now what we need to understand and appreciate from the equation are the details of what is actually happening, because we need to understand why it is called phosphorylation. So what is happening here is onto our PGA, because these naming conventions have got a meaning. When it starts off with a 3, in other words, what we are saying is that it is simply a 3-carbon molecule. But now as we move on to the next state molecule that is formed after the phosphorylation reaction, you realize that you've got a 1,3 bisphosphoglycerate molecule formed. What does it mean? What it means at first is that we started off with a molecule which had a 1-phosphate group, but now this molecule is not, the reaction is added another phosphate group on it. That is the reason as to why the reaction is known as phosphorylation. Phosphorylation refers to addition of a phosphate group to a molecule. So what and the 3 is still referring to the fact that the molecule in terms of the number of carbons there's still a 3 carbons. So the next stage now that we have is called the reduction by NADP, and what we end up with is this molecule that is known as glycerate 3-phosphate, which you can call GP3, or the other name for that is PGL. We need to understand exactly what is going on there. Why is the process known as the reduction by NADPH? So we have got our molecule 1,3 bisphosphoglycerate reacting with NADPH, and then at the end of the day is we get a PGLL, which the other name for that is G3P, and some others. What is important molecule generated, which is NADP+. Now what we seek to understand at the end of the day is the reason as to why this stage is called reduction by NADPH. So when we're saying that we are reducing, so this is, firstly let's consider our left hand side, whereby we have 1.3 bisphosphoglycerate reacting with a molecule of NADPH. What we are saying when we say it's there's a reduction that has happened, in other words, reduction is a system whereby, it's a situation whereby we have added a hydrogen ion and electrons to our bisphosphoglycerate molecule. So this is what is happening. We have added a hydrogen plus some electrons onto our molecule, and what we have at the end of the day is a PGA. What happens to our NADPH? Remember, from the light dependent stage we explained our NADPH to be an electron carrier, which is a molecule which simply harvests our electrons that we need for energy. So in other words, we've fed in our energy into this molecule, because remember what we're building at the end of the day is a high energy molecule. So we have harvested the electrons that we had from our NADP and pumped them into our 1,3 bisphosphoglycerate molecule to give us a higher energy state molecule, which is our PGL. And what is happening here to our NADPH molecule? As you can see in terms of the oxidation states, we are moving from a state whereby it is from zero to 1 plus 1. So, in other words, this our molecule, our NADPH molecule has been reduced because we are moving from a state for initially it was plus 1 to a state whereby it is 0. That is why it is called reduction by NADPH stage. And then the next molecule that we get actually supposed to be reduction of NADP molecule. And then the last stage that we get into is the regeneration of Iubp, which is actually a series of reactions taking place. Because when you get, as you can see from the cycle, when you get to this particular end, when you've got a PGL, it's a 3-carbon molecule. What is going to happen from the, you still remember the equation that I alluded to, whereby we had 6 carbon dioxide molecules are reacting with 6 Iubp molecules to give us a yield of 12 PGL molecules. But now, if you look at that particular instance, what is happening is, with this in mind that our PGL is a 3-carbon molecule, what we have at the end of the day at this exit point, 2 moles of PGL are going to react as they form 1 molecule of glucose and other sugars. But now we want to understand what is the fate, because what we are saying from this particular instance, we're just saying from the cycle, we have used 2 moles of PGL to come up with 1 mole of glucose. Now the question is, what is happening to the other 10 Iubp molecules that are remaining? In the process is what is known as the regeneration of Iubp, and it is what we are going to be looking into. And before we do that, we're just going to go through the slide bit by bit so as to understand and to capture the nitty-gritties pertaining the reaction. From this diagram that we captured, there's 1 missing molecule that wasn't included. And I've explained that when you react carbon dioxide with Iubp, what you get at the end of the day is this 6-carbon molecule, which is very unstable, with this very complicated name formed, which is unstable. So from we move on to stage number. I should have missed another slide. Okay, there we are. Stage number 1, we are saying that carbon fixation, which is carboxylation, is the enzyme that is responsible for this particular reaction, is known as Rubisco. And carbon dioxide enzymatically reacts with Iubp to produce an unstable 6-carbon molecule, which goes by this name, which has a keto group. It consists of a keto group and 2 phosphate group. And then we move on to, this molecule is highly reactive and unstable. Why? Phosphate should be a suspect. It is highly reactive due to the issue of that in its configuration there's a phosphate group, and a phosphate group is highly reactive. So this phosphate group should be the subject. The phosphate group, they fight with each other, as we explained earlier on, fight with each other for the sake of understanding and appreciating what is really going on. The molecules are highly reactive, ready to kick each other out. So number 2, what leading us to the stage we refer to as hydrolysis. What happens is addition of water breaks away the bond between the phosphate groups, and a new molecule is formed called 3-phosphoglycerate, which can be shortened to PGA. And then water responsible for breaking of the bond, subsequently adding hydrogen cation and a hydroxide on the new molecule, which was then formed. And It contains 3 carbons and 1 phosphorus group, therefore it is stable. ADP is produced as well in the stroma of the chloroplast. That is what we are supposed to know. And by the way, the Calvin cycle happens in the stroma of our chloroplast. And then stage number 3 is our phosphorylation, and the enzyme that's responsible for that is PGA kinase. And what we have is our 3-phosphoglycerate PGA is reacting with ATP to form 1,3 bis-phosphoglycerate, and we have explained the nitty-gritties regarding how the reaction actually takes place. This molecule is highly reactive, unstable. Why? ADP is formed, and then the next stage is reduction, which is simply addition of hydrogen and electron. The enzyme, which is the enzyme is GP3 dehydrogenase 1,3 bis-phosphoglycerate reacts with NADP to form glycerate hydride 3-phosphate, which is known as the PGL or the G3P. A phosphate group is kicked out. That is why at the end of the day we have got this 1 phosphate group, because it's kicked out. And NADP also produced due to the reaction of reduction of 1,3 bis-phosphoglycerate, and NADP is lost to electrons and a hydrogen ion. And then at the end of the day, on this loop, exit loop, we have seen 2 moles of PGA combining as they form the glucose molecule, which is what we wanted at the end of the day. But remember, what we are dealing with is the Calvin cycle. We want for photosynthesis, for the formation, for the synthesis of our glucose to go on. So something has to happen to these 10 moles of Iubp that we have in order for them to be processed and then react again with the molecule of what? Carbon dioxide as the former on glucose. And this is what we seek to understand in the next coming slide. And from what you see here is simply the equation that I was explaining earlier on, whereby we are saying that we're getting into the specific details, whereby we're saying when our carbon dioxide reacts with a molecule of Iubp, like our 6-carbon molecule reacts with 6 molecules of Iubp, these molecules are considered to be of a lower NH state. But remember, at the end of the day, what we want to do is to have a yield of to have a higher NH yield. So as they combine together through the help of enzymes, what we have is our PGL, which is the higher NH stage. And these figures are basically what I have explained to earlier on. And then we seek to understand what happens during the regeneration of our Iubp molecule. Now we have to start off by facts, and the fact is carbon dioxide is alluded to earlier on, has got 1 carbon atom. Iubp molecule has got 5 carbon atoms, and our PGAL has got 3 carbon atoms, and 2 molecules of PGAL make up 1 molecule of glucose. And now, so in other words, I want for us to pay particular attention to what is happening here. We said what we are remaining with is basically 10 molecules of glucose. But now what we have to bear in mind is that the molecule that we want to form at the end of the day is a 5-carbon molecule, which is known as Iubp molecule, which can now combine once again with carbon dioxide to form our glucose consequently. So what is happening here, if you consider this molecule, this is a PGM molecule. It is made up of 3 carbon atoms and a phosphate group attached to it. So then what happens, in other words, is there is an enzyme which is supposed to break the bonds and form another kind of configuration, and with the desired configuration that we want at the end of the day is a 5-carbon molecule supposed to be formed. So this breaking of bonds and formation of bonds again is a processes that energy expanding. So in other words, we need ATP. That is how the ATP comes into play. We have seen how the NADP molecule was used to reduce our molecule during that stage, the other stage of the Calvin cycle. And now we are about to see how ATP molecule is also used to form what we want at the end of the day. So considering the molecules that we have here, doing simple math, it's a total of 30 atoms of carbon. And what we want to have at the end of the day is a 5-carbon molecule. So simply what we are going to do is we are going to divide by 5. So if we go 5 into 30, it gives us 6. So we now have 6 moles of Iubp, what we had in the beginning. So we see this is how Iubp is regenerated. It's got to do with through our ATP molecules breaking and adding bonds again to form our Iubp. So what we're just going to do is to read a summary of the whole processes of what's been going on. And what we have there is that I'm going to simply read off what I've been explaining. There are 30 atoms of carbon remaining from those 2 moles of Iubp that were used to the formation of, rather the synthesis of our glucose molecule. So this 1 mole of Iubp needs 5 carbons. So our 30 divided by 5 gives us the 6 molecules of Iubp. And for that to happen, we need 6 ATP molecules are used up to form the new bonds. That is how Iubp is generated, hence the term, the Calvin cycle. And now this is our equation, ultimate equation of the light independent cycle, whereby we have seen carbon dioxide reacting with ATP and NADP to produce 1 molecule of glucose, and our ADP, which is then used in our light dependent reaction, and also our phosphate group and NADP. All of these molecules that are remaining from the glucose molecule are then used during the light dependent stage. And what we have at the end of the day is our complete equation for the Calvin cycle. We have seen 18 ATP molecules combining with 12 NADP molecules and 12 molecules of water, and 6 molecules of carbon dioxide, and giving us 6 molecules of water and 6 molecules of oxygen plus 18 ADP plus 12 NAD plus molecule plus 18 phosphates molecules plus a molecule of glucose. As you can see from here, we need enzymes. Enzymes from the light dependent stage release energy to break the bond that is there to give us those like ATP. We should get, ultimately what we get is our ADP when the bond is broken, and then in the same manner, that is how we get our 12 NADP. This inorganic phosphate combines, like here, ADP, the inorganic 18 molecules of inorganic phosphate plus 18 molecules of ADP, they give us this 18 ATP. That's how we keep the balance in the equation. So that's it as far as the light independent stage is concerned.
Bills on deck on the beat.